So imagine a really sharp force, like from a hammer. So here I'll just sort of draw a hammer, I guess. There's a nice hammer, and it hits something. Should have been a cartoonist, huh? So that hits something, and if you were to kind of think about what happened, you know, if it hits at time 0, you know, so here's t, you know, it probably creates some big force that tapers off quickly, something like that. And so, you know, in differential equations, we might model that. And if you picture something like electronics, all this happens, you know, even faster. And so it might be reasonable to model this with a very special kind of function. And so let's consider, you know, a function like this, where, okay, here's t, and what I'm going to do is go out to some value tau and make the height 1 over tau. And the reason I would do this is right, that area is equal to 1, so then I could scale such a thing, such a function, any way I want, and we can call this function d sub tau for whatever tau we pick, and that's a function of t. Now your textbook, it does the same idea. It ends up doing it this way, though. It says, okay, let's go from minus tau to tau and do a height of 1 over 2 tau. And that's fine too. It's kind of funny when you have to start treating things near 0, one-sided things near 0, like a Laplace transform that starts at 0. This one over here just takes a little more work to truly develop, but they're both the same idea. And so notice that no matter what tau is, and I could do this for either of these things, if I do the integral from minus infinity to infinity of my d tau of t dt, I always get 1. Okay, because that area, yeah, there's that. Maybe it's when I get my pencil really, my stylus really, oh yeah, there, I saw it for a minute. Not sure, you know, something about getting the stylus too close somewhere makes this thing scroll. But at any rate, so this integral from minus infinity to infinity, we get 1, and actually, you know, for all practical purposes, right, this is just the integral from 0 to tau of d tau dt equals 1. And now, though, I could create a function of this integral, and think of it that way. But at any rate, what we want to do is take the limit of this thing. So we're going to call Greek delta of t the limit as tau goes to 0 of d tau of t. Okay, and I did it again. Now let's look at the property of that. You know, right? Is if I take this integral from minus infinity to infinity of delta of t dt, well, that's just, and I can bring that limit outside, so that's just a limit as tau goes to 0 of the integral of minus infinity to infinity of d tau dt, and but we know that this part, oops, forgot my dt, we know this part is 1 for every value of tau greater than 0, and so as tau goes to 0, if you just get this sequence of 1s, 1, 1, 1, 1, well, the answer is 1. So we've created this function up here such that what we have is that this is a function that equals 0 if t is not equal to 0, and we don't really have a value for it. You could say, is it infinity? Because again, if you look at the original function, d tau of t, right, that as tau gets really close to 0, its height heads off to infinity. So what's its height? I don't know. T equals 0. I mean, you could call it infinity. In a lot of ways, it doesn't really matter. It's the fact that we just have this function that has this nice property. And what's also interesting is that if you do think of then this, so I go from minus infinity to t, and I do my delta function here of, I'll call it, I don't want to use s or something, let's use r, I guess, dr, and so here's some function of t that does this. Well, notice what happens is this thing, this f of t, it's 0, then we get to t equals 0, and from this information up here, right, it jumps up to 1, and then it just stays at 1 because the value is 0 after that. Oh, that's the unit step function, or the Heaviside function. And so what we have is that our Heaviside function is the antiderivative of this delta function. And so that's kind of a interesting connection there. So our Heaviside function is the antiderivative of the delta function. Now we often call this the Dirac delta function. Okay, but that's all it is. A Dirac delta function is really simply a generalized function. It's what we call a generalized function that might be useful for modeling things like these sudden impacts. Okay, so and just in case you all didn't know, Sudden Impact is actually the name of a movie that starred Clint Eastwood, and well, who knows, maybe you don't know who Clint Eastwood is, but at any rate, that was a movie. I don't know that I've ever seen it. I don't remember. But anyway, I digress. So we have our Heaviside function is related to the Dirac delta function this way, that if we integrate or take the antiderivative of the Dirac delta, we get the Heaviside function. If we take the derivative of the Heaviside function, which again seems like something we can't do, we get the Dirac delta function. And under our normal rules, no, we can't do, we can't take the derivative of this unit step function. under our normal rules. You have to start changing the rules a bit to really be able to talk about that. But that's how these two items are related, though, is this nice relationship right there. Okay, so we'll stop that. That's the definition of our dirac delta function, or what it is and what it can model. And we'll look at some problems involving that function as a forcing function.